Okay, so this is a supplemental page, meaning that it's not going to be on any test. So this is supplemental, not on the test. It is just for interest's sake. It's a neat algorithm that lets you find the rightmost one that's been set in a bit vector in order one time in software. So this is how to find the rightmost one in a bit vector in order one time in software. So it's easy to imagine how you could do that in order n time. You just keep shifting until you test and you find that there's a 1 in the rightmost position in bit 0. But to do this in order one time is a bit more of a trick. And it's based on a paper that I'm going to show you here. So it's based on this paper called Using Debrugian Sequences to Index a 1 in a Computer Word, published by this group from MIT in 1998. And it's a pretty interesting paper. If you like computer arithmetic and algorithms and that kind of stuff, then I'm going to do a simplified presentation of it here. So this is based on Debrugian sequences, and what a Debrugian sequence is it's an n-bit number that contains all n log n bit permutations. An n-bit number, binary number, that contains all permutations of log 2n bits. And it's probably best explained with an example. 0, 0, 0, 1, 1, 1, 0, 1. And this assumes that you can wrap around the ends of the number. And so I'm going to number the bit positions here starting from the left, and there's a reason for that that'll come up later. So this is position 0, 1, 2, 3, 4, 5, 6, and 7. Alright, and so let's enumerate all. So we got an 8-bit number, and so we're going to enumerate all the log 2n, or log 2 of 8, which is 3, so all the 3-bit patterns. So 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And now let's find where they start in this pattern. So 0, 0, 0, we can find that starting at position 0. 0, 0, 1, you can see starts at position 1. So we'll put that there. 0, 1, 0 wraps around the end. So that would start here and continue with this bit here. I'm just going to undo that so it doesn't clutter the diagram. So that starts at index 6. 0, 1, 1 starts at index 2. 1, 0, 0 would start at position 7 and wraps around to position 0 and 1. 1, 0, 1 is here. So position 5. 1, 1, 0 starts at position 4, and 1, 1, 1 starts at position 3. So let's just make a note that this assumes that it wraps around the end. And what we're going to do now is we're going to put these values into a lookup table, and this will be part of the algorithm that we develop. So our lookup table we will define as uint8 type. Let's call it lookup. It's going to have 8 values in it, and we can actually just write those in order. So 0, 1, 6, 2, 7, 5, 4, and 3. That's a brace bracket at the end. Okay, so we've got a lookup table now. It tells us where these different bit patterns are located starting from the left. Now what we're going to do is we're going to take our bit vector, we're going to isolate the rightmost one, and then we're going to multiply that by the de Bruijn sequence. And then when we look at those leftmost 3 bits, we're going to be able to tell how much the number has been shifted over, which will tell us where the bit was set in our bit vector. So let's just say that our bit vector is x. So say it's 0, 0, 1, 0, 1, 1, 1, 0. So this is pretty arbitrary. To isolate the rightmost one, there's a trick that we can do. We can do a bitwise AND of x with negative x. So we're going to do x bitwise ANDed with negative x. So let's do that here. So we've got 0, 0, 1, 0, 1, 1, 1, 0. That's our x. Negative x and 2's complement. To write that out, there's a trick. You can start from the right, and you keep going. As long as there's zeros, you just copy them down. When you get to the first one, you copy it down, and you complement all of the bits to the left of that. And that's a quick way of taking the 2's complement of a number. You could also take the 1's complement and add 1, which is what the hardware does, and it's what you usually get taught in your digital circuits course. So now we are going to, bit by bit, take the AND of those bits. So 0 and 0 is 0, 1 and 1 is 1, 1 and 0 is 0, and the rest of these are going to be 0. Because they're the complement of each other. So now you can see that we have isolated the rightmost one from our bit vector. We need the index of that. We can multiply x by the de Bruijn sequence. So we had x is 0, 0, 0, 0, 0, 0, 1, 0, and we're going to multiply that times the de Bruijn sequence, which was this. And when you just have one bit set like this and a number and you're multiplying, well, that's a 2, and multiplying something by 2 is the same as shifting it left by 1 position. So our de Bruijn number is going to get shifted to the left a number of times equal to the position of the 1 in our bit vector. And so this gives us 0, 0, 1, 1, 1, 0, 1, 0. So a 0 gets shifted into the rightmost position of the Debrugen sequence, and the rest of it's been shifted over one spot. And now what we can do is we can examine these three leftmost bits, and there will be a unique pattern there based on how many positions the Debrugen sequence has been shifted, and that's going to tell us what the index was of the 1 in the bit vector that we had isolated. So in this case we got 0, 0, 1. So if we go back up here, if we look here, we got, that tells us that it's been shifted by 1 position. If I go back to here, if instead of a 1 being set, say it had been this bit here, then our Debrugen sequence would have been shifted over 5 positions. And if that was the case, if we shifted it over 5 positions, then we would have the pattern 101 in the leftmost 3 bits. So we would find this pattern here. So what we can do is we can use our lookup table. So we can, to isolate those 3 bits, so we want to isolate the leftmost 3 bits, and the way that we can do that is we can shift right by 5. So the algorithm ends up looking like this. So the index, or the position of the rightmost one in our number, is going to be equal to the value that we get back from the lookup table at the position x and negative x times the Debrugen sequence shifted over 5 bit positions. And those are all order 1 operations. You have the negative x, which can be done in order 1 time, the bitwise AND, which most processors will do in order 1 time, multiplication by the Debrugen sequence, or you can actually use a shift instruction to do that, and then again you shift by 5 and you do the lookup in the lookup table, and that can all be done in order 1 time. So that's kind of a clever algorithm that somebody developed for doing this. And this finds the rightmost one, and if you're using higher priorities, have higher numbers, then you would actually need to flip the bits as you put them into your bit pattern, which is pretty easy to do. So in this case you would just subtract the bit number by 7 as you build your bit vector, and that would do it for you. And there's also ways to make this work for 16 and 32-bit numbers as well.